In the last lecture, we talked about type 1 and type 2 superconductors. Table 4 lists some of the typical type 2 superconductors, such as niobium tin, which is an intermetallic compound, or niobium germanate, or niobium aluminum. Niobium titanium and niobium zirconium are alloys of niobium and titanium. So, the Tc values, the superconducting transition temperatures, and the upper critical fields at absolute 0. The values are given in this table, and one can easily see that with a NBTI superconductor, it is possible to cool it down below 10 Kelvin and realize upper critical fields close to absolute 0, which is as high as 12 Tesla. So, and if we want larger values, more stronger electromagnets using superconductors, then one uses the typical material is niobium tin, which has a transition temperature of 18.5 Kelvin, and it has an upper critical field of something like 24 Tesla. So, it can be used to really produce really very high field superconducting magnets. For example, if we compare these upper critical field values with the critical fields which are of elemental superconductors, which one can see that the type 2 superconductors are much superior in performance from the point of view of construction of high field magnets, superconducting magnets. So, the three parameters of crucial, which are crucial for the performance of a superconductor, are the critical current, the critical field, and the critical temperature. So, one can see that all these values are shown in a graphical form in figure, where the current, field, temperature diagram of high field, high current superconducting alloys of niobium are shown graphically. Now, all this of course means that we have to understand the electrodynamic behavior of a superconductor. This was first attempted by the brothers Heinz and Fritz London. They were brothers H. London and F. London. So, their approach was as follows. If one sees from the Maxwell equation for a typical metal, it says that the curl E is minus B dot. This is really nothing but Faraday's law. In a superconductor, since the electric field deep within a superconductor is 0 because of high conductivity, perfect conductivity, so the curl E is also 0, and therefore, it automatically leads to the situation that B dot is 0. In other words, the magnetic induction is a constant in time. But this is just a property which flows from perfect electrical conductivity, predicts that the B field, the induction field inside a superconductor does not change in time, but Meissner effect, which was discussed also earlier, which predicts perfect diamagnetism So, the discovery of Meissner effect showed that a superconductor is also a perfect diamagnet, and this requires that not just B dot is 0, but B is 0. The induction field inside a superconductor vanishes. So, the magnetic field is completely excluded by surface superconductor currents, shielding supercurrents, which make it a perfect diamagnet. So, London's equations proposed a new behavior, electrodynamic behavior, in which the supercurrent density Js, this is supercurrent density, the Londons postulated that this Js, the subscript S means it is in the superconductor. So, the supercurrent density is directly proportional to the vector potential A of the magnetic field, where B is del cross A as usual. So, this is the definition of the vector potential, and they proposed that B is curl Js, and this was the proposal of London's to account for the electrodynamic behavior of a superconductor, which implied, in addition to perfect electrical conductivity, also perfect diamagnetic behavior. In general, of course, the supercurrent density may be written in terms of the charge carriers, whatever be the charge carriers inside a superconductor, that is the concentration of charge carriers in a superconductor. Q is the charge carried by these charge carriers, and Vs is the velocity of these charge carriers. So, if I take this and sum over all the charge carriers, then that gives you the supercurrent density. We also know that because of Newton law, m dVs by dt is q e. This is Newton's law. We can even put Qs to show that they are supercurrent carriers. Similarly, M goes as Ms. The subscript S denotes that they are the charge carriers are supercurrent carriers. So, because of this, I can write dJs by dt is Ns Qs dVs by dt, and since this is, so this is Ns Qs into Qse by Ms. So, this goes as Ns Qs square by M times E. So, if I take curl and interchange curl and d by dt, this gives me Ns Qs square by Ms curl E. And since curl E is minus B dot, so you can see that this d by dt. So, I can simplify for the case of one carrier, the current contribution is minus ns q s square by ms times b, and since b is curl A, and therefore, I can write and this is precisely London relation, the relationship that was proposed by London. This is known as the London equation for a supercurrent carrier. Now, if this is the case, we can see that curl B is mu naught J s by Maxwell equation, and therefore, taking curl on both sides, curl B is mu naught curl J s, and curl J s is given by mu naught n s q s square by m s b, and the curl B is del dot B minus del square B, and del dot B is 0 by Maxwell's equation. So, we arrive at the following fundamental relationship, namely del square B is mu naught n s q s square by m s b. This is what, suppose I define this as 1 by lambda L square B, where lambda L is m s by mu naught n s q s square to the power half is known as London penetration depth. That is why there is a subscript L here, and with that I can rewrite this as this, and this can also be in the, suppose we consider a one dimensional conductor with a component of B, suppose B is a just applied along z axis or something like that, then I can write d square B by dx square instead of del square B, and that is equal to or minus 1 by lambda L square B equals 0. Now, that is an equation which is a simple second order differential equation with the solution B equal to B x equal to B 0 exponential minus x by lambda L. So, that is a simple solution for such a equation. So, if we have, what does this mean? This means that the magnetic field within a magnetic induction field within a superconductor, within a one dimensional superconductor which extends along the x axis, is given by the value of the magnetic field at the edge of the superconductor corresponding to x equal to 0, and it times exponential minus x by lambda L. That means, the induction field decays in a superconductor. If I plot the induction field as a function of the distance with x equal to 0 here, then the value here decays exponentially. So, with a characteristic decay length of lambda L. Lambda L is the distance within the superconductor in which the induction field decays to 1 by E of its value at x equal to 0. So, it is a characteristic length over which the induction field decays to 1 by E of its value. So, that is the significance of the London penetration depth. It describes the extent to which the field penetrates the superconductor, and it gives you the value, the distance, the characteristic distance over which the induction field falls exponentially. And so, deep within a superconductor, the induction field really falls to a negligibly small value, which is nearly close to 0. The London penetration depth, one can have an idea of this from substituting the typical values, assuming that the charge carriers are electrons or some combination of electrons, as we will see, pair of electrons to be precise. Then if you put in these values, then you get the penetration depth for a typical superconductor, elemental superconductor, is of the order of fractions of a micron. So, it means that the induction field within a superconductor decays really very fast within a distance of the order of a fraction of a micron, and then it decays to 0. Now, the form of this equation, the London equation, also led London to say something more about the nature of the superconducting state. The nature of the superconducting state can be inferred from, if we assume the London following London, that the superconducting state is a macroscopic quantum state. Such that the wave function of such a quantum state is given by psi square equals ns. If we make this identification, mod psi square is ns, then this gives the typical diamagnetic response of such a quantum state, and therefore, London was led to postulate that the superconductor is nothing but a quantum state operating over macroscopic distances. This was a very startling prediction, which was verified much later. In other words, a chunk of superconductor, a long length of superconducting wire is something of macroscopic dimension, is a quantum mechanical state, unlike atomic and molecular systems, which are of extremely small dimensions, atomic dimensions, and quantum effects operate at this scale, and we cannot view these effects, realize these effects on a daily basis, but a superconductor is a state which enables us to observe quantum effects on a macroscopic everyday scale. So, that is the importance of the London form of the London equation. Next, we pass on to a consideration of the thermodynamics of the superconducting state. This is the electrodynamic behavior. In addition, we said that the superconducting transition is some kind of a phase transition. It is neither structural nor magnetic, but we would like to know what kind of phase transition it is, and so we would like to discuss the thermodynamic behavior. In order to do that, we are given a clue from the existence of the critical magnetic field. which is also known as the thermodynamic critical field. Suppose this is BC at a particular temperature T, then suppose we take a superconductor and bring it to a region of 0 field, and from there we take it to a region of magnetic field B, then the work done on the superconductor per unit volume is given by where M is the magnetization. Now, this work done may be equated to the increase in the free energy. So, in magnetizing a superconductor, in applying a magnetic field to a superconductor, we get an increase in free energy. So, the change in free energy can be written as delta F, and that is Fs of Bs minus Fs of 0, and that is equal to minus integral m dot dB. The subscript S stands for the superconducting state. Now, for a superconductor, M is minus Bs by mu naught. We saw this, how the magnetization is just given by this. So, substituting this, I get integral, so Bs square by 2 mu naught. So, this is the increase in the free energy of a superconductor. We neglect, of course, the magnetization due to the weak paramagnetism in the superconductor in the normal state. So, the free energy in the normal state can be taken to be 0. So, the free energy in the normal state is approximately 0 if you neglect the, if one neglects the weak paramagnetism. So, the Fn of Bc of course is the same as Fn of because it is non-magnetic. So, no energy change in free energy when you magnetize it. Therefore, this gives you Fn of Bc minus Fs of Bc is not 0, but it is all right. So, Fn of Bc, this is the difference in a magnetic field. So, you have the normal state and the superconducting state, and when there is a transition from this in a critical field, then the free energy of the two states will be equal at the critical field. Therefore, from this the consequence is that we have Fs of Bc equal to Fs of 0 plus Bc square by 2 mu naught. Therefore, Fn of 0 minus Fs of 0 equals Bc square by 2 mu naught. This tells us that the free energy difference between the normal state and the superconducting state is determined by the thermodynamic critical field, its square divided by 2 mu naught. So, that means that when you apply a magnetic field, this is the difference in free energy. So, this gives a clue to describing the thermodynamic behavior of a superconducting state as follows. We know how the critical field varies with temperature. We already saw that there is a parabolic law now. We can equate the free energy difference to as related to the difference in entropy between the normal and superconducting state by writing minus d by dt of Fn minus Fs, because of the connection between the free energy and the entropy. And therefore, now replacing this, and that will be minus Bc dBc by dt divided by 2 mu naught. And what is dBc by dt? From here, gives me Bc 0 minus T by Tc square twice. So, replacing here, I get Bc square by 2 mu naught into 1 minus T square by Tc square times T by Tc square. So, that is the entropy difference, and since I have a positive definite quantity here and everything else is positive, so the free energy entropy difference is positive. In other words, the normal state is of higher entropy than the superconducting state is of lower entropy than the normal state. In other words, the superconducting state is more ordered, since the entropy is connected to the amount of disorder present in a system thermodynamically. That is the interpretation of entropy. So, it says this relationship. So, this says this is greater than 0, showing that the superconducting state is a more ordered state than the normal state. Once we have the entropy difference, we can also write the difference in specific heats. Specific heat is a quantity which one can measure experimentally. So, let us go to the specific heat C n minus C s, and that will be T d by dt of S n minus S s. And therefore, making a further differentiation, we get T into minus Bc by 2 mu naught into dBc by dt, d square Bc by dt square. So, this will have, because I know that Bc is Bc 0 into 1 minus T square by Tc square. Therefore, dBc by dt is Bc 0 into minus 2 T by Tc square and d square Bc by dt square So, this will be minus T by 2 mu naught dBc by dt whole square plus Bc d square Bc by dt square. So, we can find this, and since we know dBc by dt whole square will be, one can find d square Bc by dt square from this, and therefore, we will find that at B equal to Bc, at T equal to Tc, there is a jump in the specific heat. So, this is negative, indicating that there is an increase in specific heat at the superconducting phase transition from the normal to the superconducting state. So, if we plot the specific heat from the normal state downwards as you decrease the temperature C, suppose this is the Tc, then we know that it is a linear specific heat for a metal, for a normal metal, and it decreases, and then at the transition temperature there is a jump in the specific heat of the superconducting state, and then it falls exponentially down. So, this exponential fall is something close to absolute 0. The specific heat falls exponentially to 0. This is something that cannot be understood in the light of this theory, and the specific heat goes as constant times exponential minus alpha Tc by T. So, that is the typical experimental variation, and this cannot be understood in the light of this thermodynamic theory. One has to use the microscopic theory regarding the superconducting state, which predicts an energy gap in this excitation spectrum of a superconductor. And this microscopic theory was proposed by 3 people, Bardeen, Cooper and Schrieffer. So, this is known as the BCS theory. This was, for this they got the Nobel Prize in 1957. So, the microscopic theory of the superconducting state predicts an energy gap in the excitation spectrum, which enables us to understand why there should be an exponential decay of the specific heat. We will see the microscopic theory later, but right now we will try to understand the thermodynamic behavior in terms of another celebrated theory, but which is a thermodynamic theory, namely the Ginsburg-Landau theory. We will discuss this theory because of its importance from a thermodynamic point of view of the superconducting state as a thermodynamic phase transition. Landau proposed a general theory of phase transitions, which was applied by Ginsburg and Landau to the case of a superconductor. Now, this general theory always proceeds by defining an order parameter of the transition. Now, what is an order parameter? An order parameter is defined by the fact that this is 0 for temperatures above the transition temperatures and not 0 for temperatures below the transition temperature. In other words, it can be any parameter which appears only at the transition temperature. Above it, it has a 0 value. There is no order, and therefore, the order parameter is 0, and below the temperature transition phase transition temperature, the order parameter is non-zero. Any parameter associated with the ordered state which satisfies this behavior can be taken as an order parameter. For example, in the case of a ferromagnet, the order parameter will be the magnetization, the spontaneous magnetization. There is no spontaneous magnetization in the paramagnetic state, but in the ferromagnetic state there is a non-zero spontaneous magnetization. So, the spontaneous magnetization can be used as the order parameter for a magnetic phase transition. Similarly, we introduce an order parameter for the superconducting state. Now, Ginsburg and Landau introduced this by taking the order parameter as the charge density, the superconducting charge concentration Ns, which is related to mod psi s of r square. In other words, there is a wave function, because we already saw that the superconducting state is a quantum mechanical state. So, there is a wave function associated with it, such that the square of the modulus of this wave function gives you a measure of the charge concentration, of course multiplied by the appropriate charge. So, now the next step, this is step 1 in the Ginsburg-Landau theory. The next step is to expand the free energy, because any thermodynamic theory starts with the assumption that the phase transition is a result of a reduction in the free energy. So, the appropriate free energy is expanded in powers of the order parameter. In this case, the wave function psi and its higher powers, then it is minimized with respect to variations in the order parameter. So, this minimization procedure enables us to discover the phase which has a free energy minimum and therefore is stabilized thermodynamically. So, the free energy density with respect to the unit volume is expanded and then minimized with respect to variations in the order parameter psi of r. There can also be changes because of an applied magnetic field. So, the free energy has to be written in terms of, it will have a term due to the magnetization, and then it is minimized also with respect to variations of the applied magnetic field. This procedure leads to the so called GL, Ginsburg-Landau equations, corresponding to the free energy minimization process with respect to variations, spatial variations of the order parameter as well as variations due to the field, applied field. This results in the so called Ginsburg-Landau equations, which characterize a superconductor thermodynamically, and the Ginsburg-Landau equations provide the starting point for all thermodynamic explanations of the superconducting state, which are at the bottom of, which form the basis for the application of a superconductor in technological context. So, for technical applications, the GL equations provide a convenient starting point. We will describe these equations in greater detail in the next lecture and then go on to the microscopic.